All right, everyone. Hope you're well. This is going to be our first video on gases. So we're basically finishing off with acids and bases in terms of stoichiometry. Don't fret, you'll see more stoichiometry and moles after we get the intro to gases done. For the moment, you can put stoichiometry aside. You might want to bust out a piece of paper. Today's video is going to be one of two videos this week, and it's going to be a bit more idea and concept heavy, because we need to lay the groundwork to understand the sub-world of gases, how they are slightly different when we calculated masses and moles for solids, and of course, masses and moles for solutions, which is liquids. So some of you might have already guessed that we, are definitely going to go into gases. Anyways, again, to be a little bit longer, I'm going to try to keep it a little less mathy. But of course, there is one thing we definitely need to do, and that is simple conversions. You'll see when we get there, okay? And also, please forgive me, this video is going to be a little bit story heavy because I need to connect ideas. And so grab some chips, whatever. Here we go. Please, once we do the video, speed read through the chapters, chapter 11.1, 11.7, to talk about some of the maybe smaller, not less significant, but things that may be slightly loose ends that don't really tie with the flow of my conversation that you may find valuable but might miss just from watching the video. So try at least chapter 7.1 and a bit of chapter 7.11. 11.1, 11.7. Okay, here we go. If you recall, do you remember the story that I told in class about how on Earth, right, that's you, there is pressure. There is constant pressure pressing down on you. Now, at the time when I told you this, some of the students are like, I don't feel anything on me. That's true. Well, number one, you're strong enough to withstand the kind of pressure that's around the atmosphere around the world. And number two, there's actually something inside you that's fighting that pressure. What is it? Well, it's pressure from within. Let me try to explain one more time. If this was you, okay, and of course, this is your lungs because we're talking about gases here. Okay, all around you, the air molecules, or just any molecules really, is constantly pressing down on you. You are surrounded by air molecules. So it makes sense that it's pressing down on you. What I mean by pressing down, I'm basically talking about, here's a oxygen molecule, and it is colliding with your face. Okay, here is a carbon dioxide molecule. It is colliding with your nose. Here is a, nitrogen molecule. It is colliding with your head, and it's just bouncing off. So your body is actually feeling millions and millions and millions of collisions every single second, but you don't really feel it, okay? Now, again, that's basically the definition of pressure. Pressure is essentially the amount of collisions that you feel per square meter. I believe that's the definition for atmospheric pressure. And yeah, so you should be feeling a certain amount of force, let's take that back, a certain amount of pressure on the surface of your body. But the reason that you may not feel like you need to crumple up like a piece of paper, okay? The reason why you may not feel like you have to crumble up like a tin can is because inside your body, there's the opposite force or opposite pressure or collisions pushing back out. Remember, you need to breathe air in, and it goes into your lungs and into parts of your body. The air inside your lungs, of course, and your body is essentially retaining the same amount of pressure. So it's inside your body and outside it's equal pressure, right? This is also one of the reasons why, one of the ways that you are able to breathe properly with your diaphragm if you're taking biology, but I digress. Long story short, you are constantly feeling pressure. Okay, and why am I telling you this story? It is because pressure is going to be a very important part of gases. Okay, now imagine, the story continues, if you were to take yourself out into space, what happens to you? Well, in space, the collisions are virtually nil. There's no air molecules in space. It's all gone, right? So all of this, all of these arrows that are hitting you actually aren't colliding with you. But what is colliding with you? The air inside. So what happens to you? Well, long story short, if you are thrown out into space without a spacesuit, of course, besides the obvious, like the liquids in your body and your eyeballs evaporating, which is gross, your blood, I believe it evaporates too before it freezes over. I don't know, there's a lot of interesting mechanics that would happen if your body was thrown out into space. So don't believe all the Marvel movies that you watch, okay? Those are superheroes. So your body, the air inside your body, okay, would start to balloon your body out because there's nothing fighting or countering the pushing out from inside your body, right? It's a little gross. I don't think we've ever recovered a body from space before, but if we did, you would see that their body would sort of be sort of expanded, balloon. It's a little gross, okay? Why am I talking about all these collisions? Well, I'm trying to connect the idea with collisions and this thing called kinetic molecular theory. And in short, what kinetic molecular theory means is, it's the idea that all substances, everything, so molecule-wise, whether it's solid, liquid, or gas, they are always in constant motion. All substances are composed of entities, according to the textbook, that are in constant random motion. Random, okay? You can't predict it. If people here who've seen maybe the movie Beautiful Minds with Russell Crowe, I believe there was a scene where he was trying to create some kind of amazing theory as part of a contest or part of his job as a professor while he was being schizophrenic, and he was actually trying to predict the movement of smoke or something, okay? And if you've seen smoke, let's say from, I don't know, from a pipe, smoke from, let's say, fire, you know that the smoke will sort of, as it rises, it sort of goes everywhere, right? And that is essentially kinetic molecular theory. The idea that it's too random, you can't predict it. And of course, you know, being the beautiful or the brilliant mind that he is, he was trying to predict that randomness in a certain way. Anyways, let's keep moving. Kinetic molecular theory brings us next to another statement, and that is Brownian motion. Brownian motion, which states the random movement of microscopic particles suspended in a liquid or a gas. Okay. So it's basically the same definition of kinetic molecular theory, but we are specifically talking about it in the context of a liquid or a gas. It is random, but it's not completely random because it has to be in a specific space, right? We call it random because in a solid, it's moving, but it's sort of vibrating. It's not doing anything. For a liquid or a gas, the movements are just about, it's fluid. It can go anywhere. As long as for liquids, it's within this context. For gases, it can go anywhere it wants to and continue to spread out. Okay, so Brownian motion. And from there, we can start to talk a little bit more about, well, what is fueling this motion? What is fueling motion? What is motion? All these different questions start to pop up. And we get to the concept of kinetic energy. Okay, so Brownian motion, kinetic molecular theory, every single molecule that's moving kinetic energy. Okay, basically, yeah, kinetic energy, and every single thing that's moving, every single object, every single substance that has constant random motion, according to kinetic molecular theory, must have kinetic energy, and that is energy that is possessed by moving objects. Now, that seems obvious, right? If you're moving, obviously you have energy, blah, blah, blah. We have to establish that idea so that we can continue on with the next topic. So before we go on, what kind of movement are we talking about? Okay. What kind of movement do you have to say that we have kinetic energy? The textbook talks about 3 different things. There's a bit more that we can discuss afterwards, but for now, let's just talk about the ones that are discussed in the textbook. Translational. Translational energy is basically lateral movements. For this body to move to another part of the body just exactly as it is, from left to right or right to left or up or down, down to up, we call that translational. Does that sound familiar? Remember math? Horizontal translation, vertical translation. Yeah, that's exactly what I'm talking about. The next one is rotational. And I think that sort of makes sense. If I have this and it rotates to that. So in other words, it basically rotated in a counterclockwise direction. Yeah. If I want to be more clear, see the dark one is now here, and the light one, which was to the right, is now to the left. You get what I'm saying. Rotational, okay? And lastly, vibrational, okay? Vibrational. It's literally vibrating on the spot, okay? All of these are different types of motions, and so to do any one of these, or all 3 at once, it needs a certain amount of kinetic energy. It needs a amount of energy. There are a couple of others. You know what? Save it for grade 12. This video is already complex enough. Let's move on. So now that we've talked about the different types of movements, what would happen if we added energy to these molecules? What happens when, or if, we add energy to the molecules? What do I mean by that? How do we add energy? We can't hold it in our hands, but what we can do is add heat. What do I mean by that? Increase in temperature. If I up the temperature, what do you think would happen? Going once, going twice? Well, I hope you got to the answer that if you increase the temperature, you're essentially giving it more energy. And if you give it more energy, then you're giving it more movement. But if you're giving it more movement, what do you think happens to the pressure, the number of collisions? Okay, so if we add energy, how does that affect number of collisions? Going once, going twice. If we added energy, we increase the amount of collisions. And if we increase the amount of collisions, how does that affect pressure? Do you see the chain? Do you see the connection between the ideas? Okay, the idea is this. If we up the kinetic energy, which means we up the heat, we up the temperature, that means we up the movement of the objects, which means we up the number of collisions, which means we will up the pressure. So if we up the temperature, we up the pressure. Pressure and temperature are directly related to each other. Okay? So if we're talking about temperature here, we need to also talk about pressure. So that's why I said all these stories. Okay, let's try this. I am going to clear the screen in 3, 2, 1. So let's talk a little bit about pressure. Okay, as you might have imagined, whether you are on the bottom of a mountain or the top of a mountain, depending on where you are on Earth, pressure can change. So we need a way to measure pressure. On Earth, at sea level, around the Earth, okay, we need to understand that we need a reference point. Okay, so if you're way too high or way too low, it's sort of, yeah, it doesn't help us. So we're going to measure our average pressure at sea level. And at sea level, the general atmospheric pressure that is ATM is equal to 1, because that's the simplest number we know. Okay, not 0, because if it's 0 pressure, that doesn't make any sense. So we need a number, and that's going to be 1. So we call it 1 ATM. But as time went on, there were some other units that were sort of used or discovered or found to be useful before atmospheric pressure was even established. One is the Pascal, or the kilopascal. 1 ATM would be equal to 101.325 kilopascals. Okay, so that is kilopascals. Pascal is the unit for pressure. It's a slightly different unit from atmospheric pressure. Okay. Another way we can convert this, 1 ATM, or 101.325 kilopascals, is also equal to 760 millimeters of mercury. This was, I think, even before pascals or atmospheric pressure, because back then they were able to, in a funky way, able to measure how high liquid mercury was able to rise above and sort of fight the strength of gravity. Short story, pretend you have a bowl of mercury, liquid mercury, okay? And you have a little capillary tube of sorts connected to the mercury. As you might imagine, air molecules are constantly colliding into the pool of mercury. So much so that the mercury would actually rise above because there was pressure pushing down on it. And the mercury needed a place to go. So it was able to actually escape up to a height of 76 centimeters, or 760 millimeters. So they said at sea level, the pressure was enough to raise mercury by 760 millimeters. And so that was sort of the equivalent of 101.325 or 1 ATM. There is another one. I know this is a little bit weird. There's another measurement called torr. And depending on the textbook, sometimes they use it, sometimes they do not. Torr is a sort of a slightly, I guess, archaic measure, in my opinion, but some textbooks still use it. I'd like you to be familiar with it. Yeah, I'm not gonna sort of try to explain where that's coming from. 1 millimeter of Hg, 1 millimeter of mercury, is the same as 1 torr. Okay, so just know that it's one and the same. There is one more for those people who are bikers. We rarely ever use this, or people who are mechanics here listening to this video. There is another one called PSI. 1 PSI is equal to 6,895 pascals, or 6.895 kilopascals. But I don't think any textbook really uses PSI, so you don't have to worry about it. All right? Why am I telling you all this? It is because, well, it gets even more complex. Any questions that you do in the future is always going to give you some pressure with some temperature as reference. okay? We know that pressure and temperature are related to each other. And so you know that in an experiment, okay, if P changes, T can change as well. And if pressure changes and temperature changes, that means the kinetic energy changes. That means the behavior of the molecule can change, which may make the result of a reaction slightly different. And so anytime we do some kind of reaction in the chemistry world or the scientific world, we need to make sure pressure and temperature are done in the are constant. So all the reactions are done in the exact same conditions. So we have a couple of, I guess, universal global standards that we use together. So all we have to do is say this little acronym, and the entire scientific world knows exactly what condition you're talking about. The first condition is called standard temperature and pressure. It's called STP. So if we say the experiment was done in STP, what does that mean? It means the pressure is going to be exactly 1 atm or 101.325 kPa. And temperature is exactly 0 degrees Celsius, or in the future, you'll know that we're going to use exactly 273 kelvins. We're going to learn more about this new unit of temperature in the next video. Okay? So that's number one. What's weird about this one? Why would this be weird if this is considered standard? Well, 1 atm makes sense because at sea level, that's our general standard. That's our point of relativity. But 0 degrees Celsius? Who the heck in this world considers freezing temperature to be a standard? Well, I guess some people, but I don't. Okay? And so we developed another standard that we can use that we can actually uphold and perform experiments in practically in a regular laboratory where we can sort of not have to wear parkas while we do the experiment. And that's called standard ambient temperature and pressure. That is SATP. And they're both, the pressure and the temperature is slightly different. To make it more realistic, pressure is actually at 100, exactly 100 kPa. I'm guessing it was a little easier to maintain in a controlled environment. And temperature is 25 degrees Celsius, or in this case, 273 plus 25 to 98 Kelvin. Okay, so if a question says the experiment or the gases were found at STP, you know that this is pressure, it's given, and temperature, that's given. If the question says SATP, well, you know that pressure is automatically going to be that, and the temperature is going to be 298. Okay. Any questions so far? Wait, that was by habit. I realized that you can't actually ask me or answer anything. Before we continue, or that's the end of the video, I'm going to try to do some practice questions with you in hopes that it'll stick. The first question I want to do is from page 519, number 5, page 519, numbers 5A, B, C. Number 5A, what is kinetic molecular theory? Can you recap? Kinetic molecular theory states that, or kinetic molecular theory is, the idea that all substances, any matter, has entities in it that are in constant random motion. Part B, use the kinetic molecular theory to explain the change illustrated in figure 5. And what is the illustration? We have a body of water with a whole bunch of water molecules randomly floating, but once in a while you will have water molecules escaping. Can you care to explain? You have an idea? Going once, going twice. Well, even in the coldest of temperatures, if you leave a pan of water out in the open, sooner or later you will see that the water will disappear. Why? Because it is evaporating. Well, what is evaporating? Evaporating is the constant motion of the water molecules. Okay? Once in a while, will allow one of these molecules to have enough kinetic energy to fight off the intermolecular forces that bond, so the hydrogen forces and whatnot that keep the water molecules together, escape all that and become free as a water vapor, a gas state. Okay, so in short, kinetic molecular theory states that all molecules are in random motion. During that random motion, there will be, as a result, random collisions. The random collisions may randomly allow one of the water molecules to obtain enough kinetic energy to fight off intermolecular forces and escape into the air from the body of water, a body of liquid state. There's your answer. Part C. Use the kinetic molecular theory to explain why the scent of perfume spreads more slowly outdoors in winter than it does in summer. I think that's pretty self-explanatory. In the summer, temperature is high, which means motion is high, which also means collision is high. But anyways, if the motion is high, that means we have faster spread of perfume molecules from a concentrated location. Okay. Case in point, let me tell you a very embarrassing story. My friend and I, when we were younger, I'm talking like grade school, I'm like grade 6 right now or something like that, right? We were walking down to school and yeah, we met up before because we live in the same neighborhood, walking down, and my friend rips one out. It was a big fart. It was like, you could hear it. And he wasn't even apologetic. He's like, yo, we're guys here. Burp. And as soon as he farted, instantly I smelt it. And it was so surreal. It was really bad. Yes, the smell was really, really bad, but it was way too soon, right? So we're walking, okay? He lets one out, and instantly I smelt it. And besides the fact that the smell is really bad, I was like, yo, it wasn't even 1 second. It was less than 1 second. How the heck did I smell it so fast? Little did we know, it was actually in the dead of winter. And we had these jackets on and stuff like that. And guess what? Your body temperature is 37 degrees. Outdoors, it's like 0 degrees. And what do you know about hot air versus cold air? Hot air rises. And it was the heat, the temperature of this versus the temperature outside allowed the motion of the fart to move a lot faster than the motion of the air molecules around us. And so that ziplined it, that beelined it right to my nose, okay? That's one application of kinetic molecular theory that we were like, oh my goodness, science makes sense. This was grade school. It blew my mind, okay? So even in the most embarrassing situations, you can see science. So next time someone farts in front of you, I guess the moral of the story is don't run from it. Go and smell it so that you can see science in action, okay? Did I really say that? Yes, I did. Second question for you. This is page 545, number 1. I believe this is going to be a conversion question. Sorry, not 545. Not 545. 543. Sorry, 543. 543, number 1. Convert each of the following measurements of pressure to the units indicated. All right, I want to do one conversion with you so that you know how to go about this in the future. How do I convert kPa to millimeters of Hc? Well, you know that 101 kPa, sorry, 0.325, sorry, is equal to 760 millimeters of Hg. So here's what you do. If I have 203 kPa, I'm going to multiply it by a conversion factor that will give me millimeters of Hg left. And simply speaking, if I want the unit left over, it's going to be in the numerator, and whatever unit I want removed, I'm going to place in the denominator so we can actually divide each other out. What is this conversion factor? Well, I know that 760 is equal to 101.325. So what I'm actually multiplying by is the value of 1, because 760 mmHg, 101.325, they're equal to each other. And if you have a number divided by a number that's equal to each other, that's equal to 1, right? It's a little bit of math. Let's move on. So 203 times 760 divided by 101.325. kPa is going to be divided out. And if I had a calculator available, I would write 203 times 760 divided by 101.325. That is going to be 1,522.625. If I were to give sig figs, 3 sig figs, these two don't count because they are constants. 1.52 times 10 to the 3 millimeters Hg. Shall we do one more? Let's do one more. Part 2. The textbook gives it as 1520 mmHg. That works too. 40.0 kPa to torr. And you know that torr is basically the same as mmHg, right? So again, the conversion factor is 101.325 kPa, which is equal to 760 torr. And so 40.0 kPa multiplied by, I want torr left over, I want to get rid of kPa. And if I put the numbers in accordingly, next to the unit, corresponding unit, I will get 40 times 760 divided by 101.325. That comes to 300.02, which is going to be exactly 300 torr. And that's it. Okay. So I did mean to do page 546, number 1 with you, but it's basically the same thing. Would you try these questions that I assigned in the beginning of the video? The more you do, the better, of course, but I am going to just focus on the conversions for now. Please make sure you know how to do the conversions. Being able to convert becomes very, very important in the next video when we start getting a bit more mathy. So try the questions, and we'll see you in the next video.